Stanford University.
Let's begin with a little mathematical preliminary, a few mathematical preliminaries, which if I didn't do them now in advance, I would have to do them during the course of showing you some things about string theory, and that would be a nuisance. On the other hand, there's nothing that I think you don't know well, or that most of you don't know well. First thing, just a little bit of calculus formulas, a couple of calculus formulas that are useful to have on the blackboard. If we have a function, and let's call the function x, that's the dependent variable. X is a function, and what is it a function of? It's going to be a function of a variable called sigma. Why am I using x? Why am I using sigma? Because it turns out that these are the standard notations that are used in string theory for certain functions. But they could be any functions. It could be y as a function of x. It could be x as a function of sigma. It could be f as a function of g, whatever. Right? And I'm going to allow, for the purpose of this discussion now, sigma to be a variable which runs from 0 to pi. In other words, half a cycle around a circle. So sigma is an angular variable, except it's not quite an angular variable. It's an angular variable that only goes halfway around the circle. Well, I want to approximate a continuous function by a discrete function, and eventually make my description better and better and better by filling in the axis with more and more points. That's what calculus does for you. So we replace x of sigma by x, let's call it sub I, where I runs from 1 to n. Later on, we're going to let n get very, very big. Let's think of the difference between x at I and x at I plus 1. We can call that delta x if we like. But it's delta x between I and I plus 1, or I and I minus 1, I think I made it. It's just equal to x of I minus x of I minus 1. I could have chosen it I plus 1 minus I. That's delta x. Okay? And it's well approximated in the limit where we put many, many points in there, assuming the function is smooth, in other words, assuming that the limiting function is a smooth differentiable function. It's well approximated by derivative of x with respect to sigma times delta sigma. And how big is delta sigma? Delta sigma is the sigma interval between two neighboring values of sigma. How big is that? That's the whole interval, pi, divided by n, chopped up into n little segments. All right, so this is another formula that we'll make use of. And finally, a formula, this is for derivatives, the formula for integrals. Let's first imagine adding up all the x's. Sum of all the x sub i's. We're adding them all up. What's the approximation for that? Well, if you multiply it by delta sigma, in other words, just take delta sigma, which is pi over n, and multiply that by the sum of the sigmas, this becomes, in the limit, the integral, in this case from 0 to pi, of x of sigma. We simply replace x of I by x of sigma, and delta sigma becomes d sigma. Basically, it's the definition of an integral, but I want to have these equations on the blackboard because we'll use them several times. Okay, that's the first mathematical preliminary. Let's draw a line underneath it. I'm going to try to get all the mathematical preliminaries on the blackboard over here and then use them over there. Okay, next. Supposing we have a function, now a continuous function. Actually, it doesn't even really have to be continuous, but the function, take it to be continuous, defined on the interval from 0 to pi. any such function, with a caveat that we'll describe in a minute, any such function can be Fourier analyzed, or another way of saying is it can be written as a sum of sines and cosines. Sines and cosines, and I'll write out and I'll give you examples in a moment. But before you do so, I should say sines or cosines. Before you do so, before you do it, you have to establish certain features about the functions which put them in a class which is either called Dirichlet or Neumann. Anybody know what they are? Dirichlet?
Yeah, boundary conditions.
Boundary conditions. Boundary conditions, the behavior of the functions at the endpoints, the boundaries of the interval. All right? So, for example, this function could stand for the displacement of a violin string from the horizontal. For a horizontal, well, not for horizontal, but for a violin string, you hold down the ends. The ends are firmly in place, and therefore the value of x at the ends is 0. Okay? Just because the ends are being held fixed, those are called that is called Dirichlet boundary conditions. I'll write it once, Dirichlet. Dirichlet was a Dirichlet with a T at the end. Dirichlet, of course, was a French mathematician and studied waves moving on things like strings and classified one of the boundary conditions as Dirichlet. And the meaning of that, or Dirichlet boundary conditions, means x at the endpoints, that means x of 0 equals 0, and x of pi equals 0. Now, another class of functions which are sort of the opposite in a certain sense, well, they're not the opposite, but they're just another class of functions, are described by something called Neumann boundary conditions. Neumann, of course, was a German mathematician. N-E-U-M-A-N-N. Neumann boundary conditions. And those, we're going to find, those are the appropriate conditions for discussing a string, the motion of a string. And I'll tell you where they come from as we go along. But at the moment, I'm not doing physics. I'm doing just some mathematical facts. Neumann boundary conditions are the statement that the derivative of the function is 0 at the endpoints. So let's first draw a Dirichlet function. A Dirichlet function might look like this. It's pinned down at the endpoints, and so x at the endpoints is 0. For Neumann functions, the derivative of x with respect to sigma is equal to 0. And those are functions which look like this. Let's put a vertical axis there too. Vertical axis. They don't necessarily go through 0 at the endpoints, but their derivatives go through 0. That means they have no derivative at the ends here. They're flat at the ends. Those are Neumann functions, or better yet, that's the Neumann boundary condition. Now, why would you impose one versus the other? We'll discuss that. This is clear that you would want to impose this if you had a string which was held down. When would you use this? The answer is when you have a string whose ends are not held down. But we'll come to it. Both kinds of functions can be Fourier, can be written as, yeah.
I'm just going to say, with a vibraphone or vibraharp, that's where you have resonant bars supported at quarter wavelength ends in the end.
I don't know how it works. I'll tell you where you would use Neumann Dirichlet. If you have an organ pipe, and if you close up the ends of the organ pipe, then the sound waves have to be 0 displacement at the ends. If you open up the organ pipe, then the ends, then it's Neumann boundary conditions. So, yeah.
What if the string goes up vertically at
vertical. We're not talking about strings moving in gravitational fields. Vertically and horizontally are the same thing.
No, I was talking mathematics, really. If you come up vertically, as an approximation, if it comes up vertically and then, is this a...
Oh, you mean if it has a vertical jump in it? Yeah. Of course, physicists as a rule don't like such vertical jumps, discontinuities. Discontinuities usually mean infinite energy.
Well, I was thinking of electric currents where you
What's
could
that?
have I was thinking of electric current where you could have a sharp jump.
Yeah. Yeah, but even a really sharp jump is something that, you're allowed, incidentally, you're allowed to have sharp jumps in these functions, but they have to be piecewise continuous. Piecewise continuous means they can have jump here, but for our purposes, in particular for a string to have a jump in it would mean the string was broken. Yeah, and we don't want to break the strings. Okay, next thing, Fourier decomposition, or yes, sir. Yes, John, it's Michael.
Does the open pipe satisfy that boundary condition?
What's that, the what?
The open pipe, does it satisfy that boundary condition?
Well, it's more likely to satisfy this one than this one.
I'm just wondering why it satisfies any boundary.
I'll have to think about it, and I'm not we can think about it, but I'm not prepared right now. If it satisfies anything, it's going to be this one, we come back to it. Yeah.
The pressure at the end has to be the atmospheric pressure, which is...
You're probably right. I don't want to think about it now. I don't want to get my head off. I'll give you an example of an idealized string system which does satisfy it. You have a pole over here, okay? And another pole over here put into the ground. You have a light, almost massless ring which goes around these poles, and they're connected by a string. Again, x corresponds to the height of the string, let's say above the surface of the Earth. This kind of system, if these rings were very, very light, would have Dirichlet boundary conditions. Instead of holding the end of the string down, the end of the string is free floating. Okay? So it's when the end of a string is free floating like this that Neumann conditions are appropriate. Now that's not obvious. That's not obvious. I'm going to explain the physics about why the ends of strings, freely floating string ends, satisfy this. But for the moment, we're just dealing with mathematics. Okay? All right, now, again, let's come back to the Fourier decomposition of such functions. And Fourier decomposition plays a very, very essential role in so many things, but in particular string theory. Functions which satisfy Dirichlet boundary conditions. Those can be, let's call them f of x. No, not f of x, x of sigma. Can be written as a sum from n equals 1 to infinity, okay, of coefficients, x sub n, those are a set of coefficients, times sine of nx, n sigma. Why sine? Because sines are the functions which vanish at the endpoints. Sine of nx for any n is 0 at x equals 0 and x equals pi. The most general function that satisfies Dirichlet boundary conditions, and which is continuous, and for our purposes, continuous, differentiable, all the good things, the most general function which satisfies that can be written as a sum of oscillating functions like this. Right? This is Dirichlet. What are the functions whose derivatives are 0 at 0 and pi? Cosine. Cosine nx. Cosine nx for any n is flat at the endpoints. And there are enough cosines, cosine x, cosine 2x, cosine 3x. What is cosine of 0x, incidentally? What is sine of, let's begin with sine of 0x. Why didn't I start at n equals 0? What is sine of 0x? It's just sine of 0, right? Which is 0. So there's no point in putting in a term which is 0. Okay. What about cosine of 0x? It's 1. And if the function happens to have an average, if its average isn't 0 over the interval, it will start out with a constant term which is just flat. In other words, a flat function is a good Neumann function. And so in this case, x of sigma for Neumann, x of sigma is the sum from n equals 0 to infinity, because 0 is now an interesting case, x sub n times cosine of n sigma. What about the derivative of x? Let's take the Dirichlet case. What is the derivative of x of sigma with respect to sigma? Well, if you differentiate a sine, what do you get? You get a cosine. So if a function is Dirichlet, its derivative is Neumann, and if a function is Neumann, its derivative is Dirichlet. That's a fact. Good. Now, the last mathematical fact that I'm going to put on the blackboard is a fact about integrals. Integrals of sines and cosines. Most of you know it. Anybody who knows anything about Fourier analysis knows it. If not, here's the fact. Supposing you take, let's work with the cosines. Supposing I integrate from 0 to pi cosine of n sigma times cosine of m sigma. What do I get? First, what do I get if n is not equal to m? You get 0. If n is not equal to m, you start with one cosine, and n is not equal to m, it means you're multiplying one cosine by another cosine. And as most of you know, I suspect, that if you do that and integrate it and average the product of them, you'll get 0. Okay? So this is 0 if n is not equal to m. What if it is? What if n is equal to m? Then it's just, well, then of course it's just integral cosine squared of n sigma. So how do you figure that out? Let's say cosine integral of cosine squared n sigma. What does cosine squared vary between? It varies between 0 and 1. In fact, the square of the cosine, if some cosine function looks like this, if some cosine looks like that, the square of it will, of course, wherever it's 1, it'll stay 1, but where it dips below the axis here, the square will be above the axis, so the square of it looks like this. The square of it looks like that. What is the average of the cosine? 0. What is the average of the cosine squared? A half. All right. So in particular, if you integrate cosine squared, you can just say the average of cosine squared is a half, but you're integrating it between 0 and pi. All right. So this function on the average is just a half, but when you integrate between 0 and pi, you get the width of the interval, the width of the integral, and this is just pi over 2. It's pi over 2 for any n and m. Sorry, no, for any n equal to m. Okay, so we can write down now that this is equal to delta nm, that's the symbol which is 0 if n is not equal to m, and 1 if n is equal to m, times pi over 2. Now, I made a mistake for one special case. Anybody know what the special case is? N equals 0. So let's take n equals 0. Integral 0 to pi of cosine, what's cosine 0 sigma? 1. All right. Cosine of 0 is 1. So it's just 1 d sigma, and that's equal to pi. So the one exceptional case is when n and m are both equal to 0. Okay? This is true. This is true for n. I won't bother writing it.
Is it exceptional?
I think so.
No, I was going to say if only one of them is 0, but that's okay.
Well, yeah, if one of them is 0 and the other is not, it's 0. Yeah, okay. No, then it's not exceptional that way. Except n equals m equals 0, and then we get pi, just pi. These are some mathematical facts that we will need. All right, the other thing that I had planned to write out is a bunch of mathematical facts, but I think I'll hold off on it. We'll come back to it. Is properties of harmonic oscillators. Yes, let me just write down one fact about harmonic oscillators. If you have a harmonic oscillator described by a coordinate x, then the harmonic oscillator, a Hooke's law oscillator, the coordinate of the oscillator you could write as x. Whether or not it's the same x as here, we'll come back to. But for the moment, let's just call the coordinate of the oscillator the displacement of the oscillator x. What is the kinetic energy? What's the kinetic energy of What's the kinetic energy of the point? 1/2 m x dot squared, right? 1/2 m times the time derivative of x squared. But you can always work in units in which the mass is equal to 1. You can always rescale things. You can rescale a coordinate so that m x dot squared is just, you take the m and you take the square root of it, you absorb it in here, and you rescale x. You can always choose units so that the kinetic energy is x dot squared and over 2. It's conventional to put a 2 there. That's the kinetic energy of a point mass. What about the potential energy of a Hooke's law? So this is energy. Let's call it energy. It's plus 1/2 times the spring constant. Call it kappa. X squared. What's the frequency of this oscillator? Can anybody tell me what the frequency is? Yeah. Square root of k over m. But m is 1. I've chosen m to be 1. I'm working in a formulation where m is equal to 1. So what is the frequency? The frequency is the square root of k. Or in other words, k is the frequency squared. Let's just put it there, omega squared. This is the formula for a harmonic oscillator. This is its energy, kinetic energy, potential energy. If we wanted to work with Lagrangians, we would write kinetic energy squared minus potential energy squared. Okay, that's the basic formula that we'll need for harmonic oscillators. The quantum oscillator, we will come back to. The quantum oscillator is, of course, quantized with energies in units of omega. So if you see this, you say, the energy levels of this harmonic oscillator are any integer times omega, times h bar. Right. All right, so I think we're all on the same page on that. Next question I want to address. Now this is perhaps a philosophical question, but I think we have to answer it. What is a particle? What do we mean by a particle? We're going to be talking about strings. Strings are not particles. Strings are assemblages of large numbers of particles with springs between them. So in what sense do we mean, what do we mean when we say a certain particle is a string? That raises the question, what do we mean in general by a particle? All right, so what properties do particles have? They have location, but no particle is known to be a point. In fact, no particle that is known is a point, period. No particle that we know of is a point particle. Even the electron is not a point particle. It has a little cloud of photons around it. The photons have virtual pairs. The electron, if you could look at it through a powerful microscope, would have some fuzz around it, and that fuzz would be virtual photons and virtual pairs, electrons, positrons. So an electron is not a point. Certainly a proton or a neutron is very far from a point. Those are big, gigantic objects that are, why do I say big? Big is a relative term. And for this class, protons are very, very big. So a particle is not a thing which is a point particle. It can be composite. It can be made of things. Would you take, let's take a thing which I think most of us would not call a particle ordinarily. Let's take a box filled with particles. A box, just an ordinary box, tin can, filled with a gas of a large number of particles. It has a mass. It has a position, namely the center of mass position. When we speak about the position, we usually mean the center of mass position. So here it is. Here's the thing we're talking about. Is it a particle? Of course not. It's a cup of coffee. It has a position. It has a mass. Why don't we call it a particle? Apart from the fact that it's big, and since I already said big is a relative term, so then why is this not a particle? What other ingredient do we add when we speak of particles, when physicists speak of particles? Now, I don't expect you to know the answer. I will tell you the answer. Anybody got an answer? Indivisibility. Nope. A proton is certainly not indivisible.
The stem?
Well,
If you turn it over, the coffee's going to fall out.
Naturally stable.
social waveform.
I'm not going to try it. This particle happens to have a hole in it. As a matter of fact, I'm going to make the hole bigger, and I'm going to... Okay, I will tell you what added ingredient is important, an important distinction between things which we usually think of as particles and things which we usually think of as highly composite. It has to do with their energy spectrum. And if you remember that energy is equal to mass, E equals mc squared, then it has to do with their mass spectrum. An electron has a more or less, well, it has a unique mass, okay? The electron, you cannot add to the mass of the electron. I could add to the mass of this very easily. Just shake it. Shake it and stop shaking it. Why have I added to the mass of it? Because I've put in some energy into it that's probably stirred it up and added to its energy, and energy is mass. Electrons, there is nothing that you can do to increase the mass of an electron. I shouldn't say nothing. Nothing that we can do in the laboratory at present can excite the electron into a state of higher mass. It's discrete. It's all by itself. Its energy spectrum, if you were to plot vertically the energy, here would be the electron right over there. The photon would be down at the bottom with zero mass. There would not be a whole bunch of excited states of the electron just above it. The proton does have excited states, but the excited states are pretty discretely different than the proton itself. It takes a couple of hundred MeV, million electron volts, to spin up a proton or to cause it to oscillate. So a proton also has, to some extent, this discreteness, and the excitations of it are well above it. All right? So it's got a kind of isolation in energy or in mass. What about a cup of coffee? A cup of coffee has a mass of some fraction of a kilogram. But what if I stir it up a little bit? So it's over here. It's up here at 1 kilogram, no, less than a kilogram. What about the first excited state of the coffee? If I were to cool the coffee down to 0 temperature, it would have some mass. How much energy can I add to it? I can add an incredibly tiny amount of energy to it. Why? Well, one way is just to poke one molecule and give it, but even less energy by making a sound wave through it, a phonon through it, an incredibly tiny amount of energy. And so there's a neighboring state right there, which is so close that you really can't distinguish it as a separate individual quantum state. And there are zillions of them, zillions of states very close by, practically forming a continuum of energy levels. That is, in practice, how we distinguish particles from mush. Mush can be excited by tiny, tiny little bits of energy. Particles, it takes a significant discrete amount of energy, an identifiable discrete amount of energy to excite them. That's really the only difference. Is a string, a quantum string, a particle or not? And that depends on the excitation spectrum of the energy levels above the ground state. If they're well separated for some reason, then the answer is it will behave like a particle. If they're extremely close together, so close together that the experiment, whatever it happens to be, can't distinguish them, then it won't behave like a particle. That's the characteristic difference between mush, as I said, and particles. The energy that it takes to perturb a proton is a couple of hundred MeV. Oh, some 15% of its own mass. To get the excited state of the proton, maybe more like 20, about 50% of its mass, 40% of its mass to get up to the next energy level. So that's pretty significant. What about a string, a quantum string? Well, the strings that we're going to talk about, the particular ones we're going to talk about, the separation between the first string and its excited state is more like the Planck mass. And that's a huge mass from an experimental point of view, so huge that we have no hope of, in a laboratory, exciting the excitations. So that's why we call strings particles, yeah.
So is this like an issue of scale then? Because if you zoomed in, you would see those different energy levels being far if you're looking close enough.
The energy levels are the energy levels. If you zoomed in, you might be able to see that it was made out of a lot of pieces, but nevertheless you would discover that even though it's made out of a lot of pieces, to excite them would cost a very large amount of energy on the scale of particle physics energy levels. In other words, if you were to try, if an electron is truly a string, and its mass is what? Half an MeV or something like that, and the excitation energy to rotate it or to vibrate it or to do anything else to it is the Planck mass, which is how many times bigger than the electron? I mean, 10 to the 23, 10 to the 24 times bigger. So there's a big gap in the spectrum. The existence of gaps in the spectrum is what defines, well, makes particles different than, how about a violin string?
Very little.
Very little energy by comparison with its actual mass. If the violin string is made out of catgut, what do they make violins? They still make they still kill cats to make violins? Yeah, okay. You know, less than a gram, I don't know what, but it's, it's a significant mass. And the energy that it would take to excite 1 quantum worth of energy to that violin string, when translated into mass, is unmeasurably small. So you've got a lot of quantum states in a tiny little interval. A violin string is not something we would call a particle. Okay, so now we have to begin to explore the mathematics. We have the mathematics on the blackboard. I suppose we should say we're exploring the physics, but the physics is fairly mathematical.
So a photon is not a point particle?
A photon is a point particle. It's not a question of point. It's a particle. There's no similar particle with a mass very close to it.
No, I was agreeing that it's a particle,
Yeah.
but the question is whether you said none of the particles are point particles.
No, a photon is not a point particle. A photon can dissociate into an electron and a proton, and a positron, not a proton, an electron and a positron. So if you were to look at a proton carefully, you would find out it's also a fuzzy structure with electron-positron pairs in it, more virtual photons. It's pretty darn small, but not infinitely small. And it's even measurably, it has measurable size to it. You can actually measure the size of it. The fact that an electron, for example, is not a point is associated, among other things, with its anomalous magnetic moment.
Does the photon size depend on its frequency?
No, not in the correct definition of it. No. Its wavelength does, but not its physical size. Right. Okay. Now, we talked the last time about describing systems at very, very large momentum. This is an important part of the logic of the approach to string theory we're going to take. It's called the light cone frame or the infinite momentum frame. And I'll just remind you for the moment, we could come back to it at some later time. But at the moment, the main fact that we established or that we talked about last time is that if you take a system which could be highly relativistic, what it means to me highly relativistic now, I mean that it has parts, pieces, which move relative to each other with close to the speed of light. Okay? A baton twirled around so fast that the ends of the baton are moving with close to the speed of light. That's a very relativistic system, and the question is, can you in any sense at all describe it using something like non-relativistic physics? Right? If the baton is moving slowly, so that all parts of it are moving with only a small fraction of the speed of light, then of course you use non-relativistic physics to describe it, but it's an approximation. It really, and as it spins faster and faster, as the parts of it get up relative velocities relatively close to the speed of light, that approximation breaks down. It's not a good approximation, so it's in no sense exact, even if the baton, if the center of mass of the baton is at rest. The issue of using non-relativistic physics to describe the relative motions of the pieces of it is not a question of whether the center of mass of it is at rest. It's a question of the relative motions. So there's no good approximation, no good non-relativistic approximation to a baton which is spinning fast enough that its parts are in relativistic motion relative to each other. On the other hand, the trick that I showed you last time is exact. It's exact in the following sense. You could take the baton twirling around an axis going in this direction altogether, and now boost it. All you have to do in order to bring it into the non-relativistic form that I talked about last time is just boost it to a momentum where the momentum of the whole thing is much larger than the momentum going around in the plane. Or equivalently, it's much more relativistic along the axis that you boosted it than it is in the other directions. Then the formulas I showed you last time become exact. And what do they say? They say that with respect to the two-dimensional motion in the plane perpendicular to the direction that you boosted it up, the description is completely and exactly non-relativistic. So that was the trick that we used, or that we're going to use, to describe the properties of strings. And it's that trick which gives me the courage to explain it to this class, because I wouldn't try to explain it in the fully relativistic form. Yeah.
Last week you referred to the infinite momentum.
That's what I'm talking about.
Yeah, so if it truly was infinite, then that would imply that it's traveling at the speed of light. Are you just slightly off?
Slightly off. Slightly off. Do you want me to go through that again just very briefly? I don't know.
So I understand the concept. It's just a question whether it's truly infinite or just really, really big.
No, you take limits. You define things which have limits. All right, let me show you the sorts of things you can define which, yeah.
What's the axis that the baton is rotating on?
You just pick an axis. Any axis. Any axis, no matter how the system is moving, pick any axis and boost it along that axis.
What if it's being boosted along the same axis that it's rotating, or perpendicular to it?
Well, if it's rotating this way, the axis is that way.
No, what if it's being boosted in the same axis that it's rotating?
Then it's moving this way. It still has a non-relativistic description. What it would look like non-relativistically, from the non-relativistic point of view, is a rod which is doing this, projected onto the plane. The projection onto the plane is non-relativistic. And the curious thing about strings is it's completely enough to know their projection onto the plane to know everything about them. This is a bizarre and interesting fact about strings, that they do not have any independent coordinates. If you boost them along an axis, they have no independent degrees of freedom along the axis. All the degrees of freedom are perpendicular to the axis. It's a rather remarkable fact about them.
Amplify that. They have no. That means they can't arbitrarily move in that.
They can't arbitrarily move in that direction. Their motion in that direction is completely determined by their motion in the other directions. Yeah, that's
Trapped it in a sandwich sort of.
Well, they are trapped in a sandwich in that direction, but it's more than that. It's not just that they're trapped in a sandwich, that their motion, well, first of all, they're Lorentz contracted. All right. But if you find examined within that Lorentz contraction, yes, they would be moving, but their motion is completely and entirely dictated by the motion in the other directions. That's a curious fact.
Is that the source of the holographic principle?
Yeah. Well, it was one of the things. It was one of the things that the speculation began. Yeah, it is. Yeah, it is closely connected with that. And I don't think we're going to try to get into that now, for sure. Instead, we're just going to. Well, all right. Let me just remind you about that light cone story. Let's spend 2 minutes at it. If you take any system, collection of particles, moving, doing whatever they're doing, it has a center of mass. In the frame of reference at which the center of mass is at rest, it has an energy. That energy is called its rest energy. And it's the thing which, when divided by c squared, you call the mass. Multiplied, divided. All right? The energy at rest means the energy when its momentum is zero. In a frame of reference in which its momentum is zero, that's called the rest mass. It doesn't have to refer to a single particle. It can refer to any system, whatever, in the frame of reference in which it has zero momentum. In other words, in the frame of reference which it's at rest, in that frame of reference, its energy is called rest energy or rest mass. Okay, so it has a mass. That mass is in general composed not only of the masses of the constituents, but the relativistic motion, the kinetic energy, and even their relativistic kinetic energy, whatever it is, it all adds up to the mass. Now, what if it's moving? If it's moving, it has an energy which is not just m, it's the square root of the momentum squared plus the mass squared. I've set c equal to 1, speed of light equal to 1. That's the formula for the energy of it. And let's write that in the form square root of pz squared. That's the direction we're going to boost it along. Plus, I could write px squared plus py squared, but I'm not. I'm just going to write p squared. Well, let's just call it px squared. Why not? Px squared plus py squared. Plus m squared. When you boost a system along an axis, let's say the z-axis, the other components of momentum don't change. So as long as these components of momentum are finite, you can always make pz much bigger than anything else in the problem, bigger than px and py, and much bigger than m. And in that limit, this becomes equal to pz plus px squared plus py squared divided by twice pz plus m squared divided by twice pz. What I've done is expand this quantity here, thinking of pz as the big thing and the rest of it as being much smaller. And this is what you get. Right? Now, first thing is, well, this does not look like it has a good limit as it stands when pz gets large. First of all, it gets large, it gets infinite. All right? But what is this infinity? This infinity is notice that this infinity does not depend on the x momentum, the y momentum, or even all the internal motions which are making up the mass. It's just a constant which doesn't depend on the internal structure of what's going on inside the object. It's just the momentum. You can subtract it off. This is a rule. If you have a conserved quantity, a quantity which is conserved and which, whatever it is, you can subtract it from the energy because in the end of the day, the only things you're interested in are energy differences. Generally speaking, at least before you worry about gravity, the only things we worry about energy is energy differences between systems. So you can either subtract it off or bring it to the left-hand side. You can write E minus PZ. And not worry about adding the PZ there because it simply never contributes to differences of energy of different things. For example, if this were an atom might decay. What an atom does when it decays is related to the energy difference between the states which decay. This, as long as the atom's momentum along the z-axis doesn't change during the decay, this term here doesn't amount to anything. Now what about the PZ in the denominator? Why is that there? Keep in mind that energy is related to time. That energy is Hamiltonian, and Hamiltonian in quantum mechanics has to do with the rate at which the wave function changes. Energy is Hamiltonian, and Hamiltonian is I d by dt. The time derivative of the wave function. Why is the right-hand side going to 0? If the right-hand side is going to 0, the left-hand side must be going to 0. In other words, the wave function must be changing very, very slowly for a particle moving with a large momentum. The internal wave function, the wave function having to do with its internal motions. Why is it that the internal motions look like they're going slow? Time dilation. Time dilation. So what you want to imagine then is you want to rescale the time. The faster the system goes down the z-axis, the slower its internal motions. But we don't want to throw away the internal motions. We want to keep track of them. We want to understand them. So we rescale the time. In other words, we go to a time variable which, as we boost the system, we go to a time variable which is suitably redefined so that the internal motion, if it was an atom, we would want to rescale the time so that the atom, so that the rate of revolution of the electrons around the atom would not go to zero. And that simply means throwing away the pz in the denominator. The pz is the time dilation factor. If we don't care about it and we want to speed up everything by going to a new time variable, all we have to do is throw away the pz in the denominator. I suppose that's equivalent to multiplying by pz. And now you see we have an expression on the right-hand side which does have a limit as pz goes to infinity. It's the Hamiltonian, or the energy function, which keeps track not only of the internal motions, but the motions along the x and y direction. The motions along the x and y direction, as well as the internal motions, are kept track of by a Hamiltonian over here, and it has a nice limit as pz goes to infinity, number one. Number two, it looks very non-relativistic. The sums of the squares of the momentum, components of momentum, or the square of the momentum divided by 2, that's the yeah.
What happened to the peculiar PZ?
The what?
Peculiar PZ.
It's dropped out.
The individual component? Well,
No, we have to worry about the relative PZs to some extent. If the system is composed of a bunch of parts, the other degrees of freedom that we have to keep track of is the ratio of momentum along the z-axis of the different parts. But in string theory, you don't have to worry about it. This is quite a marvel of string theory. You don't ever have to worry about it. It's all constrained in the...
But it is missing there.
It is missing there. Yeah, well, it's not missing here because here I'm thinking about a total system. But if the system is made up out of parts, then each part would give a contribution that looks like this.
Well, yeah, last week you were summing, so I think parts.
Here I've written the expression for the entire composite system, okay? But the composite system of made of parts, this would be the center of mass motion. This would correspond to the center of mass motion. The center of mass motion in the two-dimensional plane. If the system is made of a bunch of parts so that the p's here are sums of momentums of other particles, then yes, in principle, you should have to worry about the relative components along the z-axis. And if you really had to worry about them, it would be very complicated. String theory, for magical reasons that are only partially understood, but no, they're understood, but still a little bit magical. The relative motion of the parts along the z-axis is completely constrained and completely determined by the other motions. So you don't even have to think about it. Just throw it away. Don't worry about it. It's not intuitively obvious, but it is true. Okay, so the main message here is that the physics of a very fast-moving system, as it moves in the perpendicular plane, has the exact, this is not an approximation, exactly has the form of two-dimensional non-relativistic physics. But what you have to keep track of is that the portion of the energy which is independent of the state of motion, the thing you would non-relativistically think of as the binding energy of a system, just the energy at rest, is not proportional to the mass in this formulation, but is proportional to the square of the mass. Okay, so that's a review. That's a 1-hour review. I will try not to make 1-hour reviews for everything we do. But I thought this time it was worth the effort. Okay, in fact, I don't even think we've quite finished what we said the last time. Let's go on. Let's go on to strings now. The right model for what we're talking about now is strings moving in 2 dimensions, all right, in a plane perpendicular to the direction of the large momentum. So let the large momentum be along the perpendicular to the blackboard. Then we want to make a model of a relativistic string which is wiggling around, moving, stretching, doing all the things that, strings do, but moving only in 2 dimensions. All right, to do that, again, I think I'm still reviewing, but I think it's worth it. We think of the string as a collection of mass points. Well, we can begin by thinking of the string as a collection of mass points. We're just going back to this approximation here. Capital N mass points, capital N mass points, N minus 1 springs between them. Think of a string as a collection of mass points with little springs between them. N minus 1 springs, okay? And an energy, let's write down its energy. This is now non-relativistic physics. Each particle has a kinetic energy. It's a sum of all of the particles. The kinetic energy is x dot squared over twice its mass. No, times twice its mass. No, times its mass over 2. I'll get that right eventually. Mass over 2. This is the ith spring. And when I write x here, I mean you have to add, every place I write x, add in also y. X goes to y. There are 2 directions that everything can move in, and I'll call them x and y. I here does not stand for x and y. It stands for which particle along here we're talking about. Same thing, plus my dot squared over 2. That's the kinetic energy. And what about the potential energy? The potential energy is something like kappa times xi, or we could call it delta x. Did I call it delta x before? Yeah, delta x. Let's just call it delta x. Delta xi squared over 2, where kappa is the spring constant between the springs between neighboring mass points. That's the energy. What about the Lagrangian? It's the difference. This is kinetic energy, potential energy. Lagrangian is kinetic energy minus potential energy. So we might want to write that down at some point. And exactly the same kind of expression, except where x everywhere is replaced by y. That's a string of point masses. Now we want to take the limit in which n goes large. So first of all, we need a parameter to label the positions, or to label the mass points. That parameter will take to be called sigma, and it goes from 0 to pi. That's arbitrary. I could let it go from 0 to 1. I could let it go from 0 to 2. I could let it go from 0 to 2 pi. It's just a labeling device. We label going from 0 to pi. The reason for labeling from 0 to pi instead of from 0 to 2 pi is because we're going to save going from 0 to 2 pi for closed strings, rubber bands. Think of this string as a rubber band that's been cut open and has 2 ends. Right? A rubber band which is closed together will allow to go from 0 to 2 pi. So it's just an arbitrary reminder that this is not a closed cyclic string. We'll do closed cyclic strings too. Okay, now what about the masses? As we let n, we want the mass of the whole string to remain fixed. If each mass point weighed a gram, and I let the number of mass points go to infinity, what would happen to the string? It would get incredibly massive. That's not what we want to do. We want to keep the mass of the whole string fixed, but subdivided into smaller and smaller pieces. So that means that the mass should go as 1 over n. In fact, I think we can just let it be 1 over n. We could let it be something else over n. We could let it be 2 over n. This is actually a choice of units. This is an arbitrary choice of units. In fact, all the choices I'm going to make now can be absorbed into units. So we let the mass go to as 1 over n, and what will the total mass of the string be? Now, oh, I'm sorry, just a moment. Let me go back a second. This mass here is not the true mass of the mass point. It's the non-relativistic analog mass. I shouldn't call it m, because then you'll identify it with the relativistic mc squared mass. Let's just call it mu. Mu stands for just a parameter, and it's the analog mass of the, all right, so we'll let mu be 1 over n. What would the total analog mass of the system be? 1. Okay. So this is a string with analog mass 1. If you go, all right, let's just leave it at that for the moment. With analog mass 1. What about the spring constant? What happens if you have a bunch of very, very stiff springs? Imagine you have a bunch of very stiff springs, and because of that, you can't stretch it very much. Now we combine in series a large number of these springs. What's the spring constant of the whole thing? Is it easier to stretch or harder to stretch? It's much easier to stretch. The spring constant of the composite spring, the composite spring, is like 1 over n. 1 over divided by the number of, the meaning of that is if we want to keep the composite spring fixed, then we have to let the spring constants of the individual little springs here get large or small? Large. Large. If we have a rubber band and we stretch it, it might have a Hooke's constant of some normal number, easy to stretch. But if you try to take 2 of the neighboring molecules and stretch them, I guarantee you would have to put in a lot more force to stretch it between 2 neighboring molecules. So the spring constant, K, I think I will take to be, let's see, n, this is arbitrary, this is convention. K equals n over pi squared. The pi squared is put there only for the purpose of minimizing the number of pi's and formulas at the end. If you don't want to worry about the pi's, just ignore them. They play no essential role in anything. I put them in order to get rid of pi's at some later stage, so don't worry about them. I set nothing equal to 1 except 1. Sometimes I set some things like 3 equal to 2, but 1, not 1. Right. I checked. The normalization I want is the spring constant as well, but you can ignore that. All right, let's rewrite these things as integrals using exactly the formulas we have up there. Okay. Oh, we need one more formula. Delta sigma is equal to pi divided by n. I think I actually have that up there, do I? Yeah. Delta sigma is pi divided by n, taking the pi interval and breaking it up into n little pieces. Okay, let's take the kinetic energy first. The kinetic energy is going to be 1 over n times the sum of xi dot squared. I'm only going to do this for kinetic energy, and then I'll tell you what the answer is for the potential energy. All right, now 1 over n, let's see, 1 over n is delta sigma over pi. I've just divided this equation by pi, so let's see. So this is equal to sum delta sigma 1 over pi times xi dot squared. In fact, I want xi dot squared over 2. So that gives me a 1 over 2 pi out here. But now we use the connection between integrals and sums. A sum times delta sigma is the same as an integral. So this just becomes integral 1 over 2 pi the integral of derivative of x with respect to sigma squared, with respect to time squared. Derivative of x with respect to, let's call it tau squared. Tau is time. Tau is this analog or this time that appears in this in these light cone or infinite momentum frame physics. X dot means dx dt or dx d tau. Sum over sigma times a function is simply the integral. And where does the integral go from? The integral goes from 0 to pi. That's the kinetic energy. What about the potential energy? I'm going to tell you now what it's equal to. You can work it out yourself, use exactly the same things. The new thing that we need, we have delta x here, and delta x is related to the derivative of x with respect to sigma, right? So the other term that we get here is plus derivative of x with respect to sigma squared, all times d sigma. Have you seen the energy function like that anywhere before?
Simple harmonic.
If instead of calling x, x, I called it a phi, and instead of calling sigma, sigma, oh God, I would call it x. In other words, if I thought of sigma as a line in space and x as a field, this would be the energy of a simple wave field. A simple wave field and it would satisfy a wave equation. This physics here is exactly the same physics as all wave-like physics. Waves run up and down this sigma interval. Now, the only thing that you have to keep track of is what happens, let's suppose we have a wave. Goes from 0. And supposing we have a wave. The wave either moves to the left or the right. What happens to the wave when it gets to the end? It doesn't keep going. It bounces off. The boundary conditions, either Dirichlet or Neumann boundary conditions, will cause the wave to bounce off. Do you know what happens to the wave when you have Dirichlet boundary conditions? Yeah, it gets flipped over. It gets flipped upside down in order to keep the field here. What happens with Neumann boundary conditions? Then it just reflects with the same, it just reflects left to right, but it doesn't reflect up to down. All right, so that's the basic wave equation. We could write down the wave equation that corresponds to this. How would you write down the wave equation? Well, you'd write the Lagrangian. The Lagrangian is kinetic energy minus potential energy. And then you would work out Lagrange's equations. Lagrange's equations would just be a simple wave equation. I'm not even going to write it because we're not even going to need it. But it would just describe waves moving up and down and reflecting off the ends.
What was tau? What was tau?
Tau is time. Okay, I'll tell you exactly what tau is. Remember that we had to rescale the time because of the slowing down of clocks. Okay? Tau is really proper time. It's time, the time of a clock that's moving with our infinite. Imagine there's a clock that we boost together with the system. That clock slows down, so we're not measuring real time in the rest frame, but we're measuring, and that's the system of interest is moving next to the clock, and so we can compare the internal motions with the clock of the system. That's what this tau is. Okay, that's what this tau is. So it's time except slowed down so that we can keep track of the time-dilated internal motions. Okay, good. But that's what tau is. Okay, it's proper time. But you can just think of it as time from the point of view of this non-relativistic picture. All right, so that's the energy of the string. And it has some energy. If the string is at rest in this plane, in other words, if it doesn't have any net motion in the plane, then its total energy will be the square of the mass of the string. Okay, so we'll eventually use this formula here to identify this energy with the square of the mass of something. We'll come back to that.
A question on mu again. Mu is that the mass
Of each little
relativistic
point
mass?
here.
Sorry,
Of each point mass.
and it's not m because m is the rest mass and this is.
Yeah. It's a complete analog object that we don't even need to specify. We can just write down this formula here. We just write down this formula. Yeah.
Does that quantity have a name, E minus PZ times PZ?
It's called the light cone energy. Yeah. The reason I don't want to call it light cone is because it has nothing to do with cones. It's a misnomer.
Well, no, there's a picture where you rotate the axes. You get the same result that you've gotten, but some people find it.
No. The point is cones. These are not light cones. Cones look like this.
These are the 45-degree angles instead of the.
Right. Those aren't cones. Those are wedges. Cones around like that.
X, Y, and Z. So the surface of revolution of the.
It's not a surface of revolution. It's a light front. The right word would be light front.
Yeah,
It's the wrong terminology.
boosted direction is not a cone, right?
Right. It's two light planes intersecting. Well, don't worry about it. I purposefully didn't want to get into that. Right. There's no point in giving you wrong terminology and then explaining why it's the wrong terminology.
My picture of a 4D or 3D cone is an expanding sphere,
This is not what this is.
but this is not that.
Not that. Right. Got nothing to do with cones. As I said, it was a misnomer. Light front would have been a better word.
But didn't Dirac use the term?
I don't think so. I'm not sure. I don't know. I don't think so. No.
He just did the transformation.
Right. He did have light cone coordinates, but his light cone coordinates were like cone coordinates. He also talked about something which I would call light front coordinates. And that was this. So let's not belabor it. Okay. One last point before we. Well, I think all of this we went over last time, and I go over it more completely now. Now I think I start with something that we didn't go over last time. I don't think I did anyway. Did we talk about the boundary conditions at the end of the string and why they're Neumann and not Dirichlet? Good. Let's do that now. This is, okay, let's leave this up on the blackboard here. But now we want to come to boundary conditions. We want to come to exactly this issue. Oh, incidentally, let me reiterate again. There's another term, and the other term is of the same form except with y replacing x. Okay? The motion of the string involves knowing both x and y are as a function of sigma. A point on the string is labeled or is an x and a y. Okay, so we have both of them, and we mustn't forget about them, about the two coordinates. Incidentally, real string theory often makes use of many more coordinates. Okay? The many more coordinates would just go into x, y, give me some more letters. Don't use z because we already use z, w, v. And so forth. Gamma, Aleph. All right, let's talk about boundary conditions on the ends of strings. The boundary conditions are actually determined by nothing more complicated than Newton's law. Now you say, why are we allowed to use Newton's law? We're talking about relativity. Well, it's because of this two-dimensional analogy. In the two-dimensional motion of the string, Newton's laws are correct. Now, Newton's laws applied to what? Newton's laws applied to the mass points. Newton's laws applied to the mass points tell us how the mass points accelerate given the force on them. What's the force on a mass point? Now, a typical mass point is being pulled from the left and it's being pulled from the right. So the forces, they won't necessarily balance, but it will be getting a force from the left and a force from the right. There are two special points which are only getting forces from one side and not the other. Those are the mass points at the end of the string. Okay? So let's concentrate on the mass points at the end of the string. And then here's the last point on the string, the ultimate point on the string, that's n, and here's the penultimate point, n minus 1. And they're connected by a spring. Now, what is the force, the x component of force, on the end point of the string? Hooke's law. Hooke's law tells you that the force on the end of the string is the displacement or the distance between the nth point and the n minus first point. In other words, the force on the string, the force on the nth point here, is proportional to delta x. The last, let's just call it delta x, but it means the separation between the nth point and the n minus first point. Okay? That's the force on, oh, sorry, what about the spring constant? The spring constant, K. And if you remember, K is very large. It grows like n. I won't bother putting in the pi's. So the force on the end of on the last molecule on the chain there is delta x. It scales like delta x times n. Now, what is delta x? Delta x is approximately, and in the limit of a large number of points, it becomes exactly the derivative of x with respect to sigma times delta sigma. And what is delta sigma? Delta sigma goes like 1 over n. So the n's are going to cancel. I don't care about the numerical constant factor. The force on the end of the string is going to be proportional, let's just put proportional, to the derivative of x with respect to sigma. What is the derivative of x with respect to sigma? It's the amount that the string is stretched near the end. It's the stretching factor near the end. If the x d sigma was 0, it would mean that the nth point and the n minus first point are right on top of each other. If they're separated, then there's a dx by d sigma. Now, what does that have to equal by Newton's equations? By Newton's equations, it has to equal the analog mass times the acceleration, m times, let's call it x double dot, the acceleration. But what is the analog mass? This isn't m, this is mu. But what is mu? Mu, because we've chopped up the string into lots of little pieces, the end point is very, very light. It has a mass which is only 1 over n. Well, now we have something a little bit bizarre. If I multiply this by n, let's multiply it by n. Let's get rid of the intermediate thing here. Multiply it by n. We find that the acceleration will go off to infinity as n gets larger and larger. Okay? The acceleration shouldn't go to infinity. That doesn't make sense, that the acceleration of the endpoint of the string is wildly, wildly violent. The answer is that the right boundary condition at the end of the string is Neumann boundary conditions. So in order to prevent infinite accelerations, which are quite unphysical, in order to prevent the string from having an infinite acceleration at the endpoint, you impose Neumann boundary conditions. The x by d sigma is 0 at the endpoints. This was, in fact, the original argument about all of this. It was at this level that it was first understood. Okay, so now we have a fairly complete system, a system with a Lagrangian and well-defined boundary conditions. And the question, which we will take up after about 5 minutes, is how do you do the quantum mechanics of it? That's what we're after. We're after the quantum mechanical energy levels. We want to compute the quantum mechanical energy levels, and having computed the quantum mechanical energy levels, we will know something about the masses of these objects. That's the goal. So we can throw away everything else off the blackboard and say, here is a system. It's a classical system at the moment. How do we make quantum mechanics out of it, and how do we find its energy levels? Now, what do you do to study this string, and in particular, to study it quantum mechanically? Well, the first thing you do is you write x as a sum over cosines. Remember what x is. X is a function of sigma. So is y. X is a function of sigma. Y is a function of sigma. Sigma goes from 0 to pi. What can we do to make a concrete investigation of this? We can Fourier analyze x. Neumann boundary conditions mean cosines, and so we write x of sigma in this form, also y of sigma. And then we take these two expressions, let's concentrate on x, and we plug them into the Lagrangian. Or the energy, it doesn't matter. We plug them into the energy or the Lagrangian, into the kinetic energy and the potential energy, and we redescribe the system in terms of the kinetic and potential energy of a set of new degrees of freedom. The new degrees of freedom are just these xn's andyn's. So that's straightforward. Let's begin with the kinetic energy. Let's see, I don't think we need what's up above. So let's pull it down and start with the kinetic energy. I'll work it out for you, and then maybe we'll do the potential energy too. Once we have that, we'll have something that we can work with more easily than this form here. Okay, so we take xn, we write it this way. What's xn dot? Dot meaning time derivative. Sorry, not what's xn dot. What's x dot? X dot of sigma. X dot of sigma we just get by differentiating this. Now the cosine of n sigma doesn't depend on time at all. It's just the cosine of n sigma. It has no time dependence. Does this have time dependence? Yeah. Something has to have time dependence. The string is going to wiggle. What has time dependence is the Fourier coefficients. The sigma dependence is coded in these cosines. The time dependence, if x is also a function of time, in other words, it's a wiggling string. It's a wiggling string. The position of every point on it is time dependent. The string wiggles. Where do we put the time dependence in these formulas? Well, we put them in here. So think of the xn's as being objects which have a time dependence. Okay, how about x of sigma dot? What is that? That's going to be sum on n. We're just going to time differentiate. We're going to differentiate this with respect to time, term by term. So this is n equals 0 to infinity of, I'll write it as xn dot, the time derivative of xn, times cosine n sigma. Now let's write the kinetic energy. To write the kinetic energy, we first have to write the square of this. This is the same as dx d tau at point sigma. All right, we have to square it. To square it will give us a double sum. So dx by d tau squared will be a double sum, a sum from n equals 0 and m equals 0 to infinity, m equals 0 to infinity, x dot n cosine n sigma. I've just rewritten this, but then what do I multiply it by? I multiply it. Should I do this in 2 steps? No? Okay. xm cosine m sigma. All right, so it's xn, let's group, xm dot. Let's group them together. xn, xm dot, cosine n sigma, cosine m sigma. But now we're also instructed to integrate it over sigma, integral d sigma. The only sigma dependence is in these cosines, so we can bring the integral over to here, d sigma, and the last step is to divide by 1 over 2 pi. The 1 over 2 pi is a convention. It's a convenient convention. Okay? How about this integral? The integral has 2 kinds of terms. It has terms with n and m not equal to 0, and other terms, and another term with n and m equal to 0. We have to be a little bit careful about them. First of all, after we've integrated over sigma, there will be no terms with n not equal to m. Okay, so in other words, we're going to get a single sum, not a double sum. What will be in the single sum? It'll be 1 over 2 pi. Now, the first term is going to come from n equals 0 and m equals 0, and that is just x0 dot squared divided by 2. No 2. No 2 at all, not even any pi. Yeah, 2 and no pi. Where did that come from? It came from the pi canceling the pi downstairs. That's it. Right? What is this? What is this x0, incidentally? Do you have any idea what x0 stands for? It's the average position, right? But that makes it the center of mass position. The center of mass position of the string. The string, in addition to everything else, in addition to all of its wiggles, it has a center of mass motion. It has a center of mass, which is its average position. This is just the kinetic energy of the center of mass. Everything else is associated with the internal vibrations and the internal motions. This is the piece that has to do with the overall motion of the string. So x0 and y0 are nothing but the center of mass. Okay, let's suppress y and just work with x for a minute. Now what about the other terms? The other terms are a sum from n equals 1 to infinity. Let's see what they have. Let's put them in. Plus 1 over 2 pi xn dot squared. There are no terms with n not equal to m. And then what's the integral of cosine squared of n sigma? Pi over 2, right? Pi over 2. So the pi's will cancel, and we'll get an extra factor of 2 downstairs, which will make it overall a 1/4. Okay, so this is center of mass, sum. And this here has to do with the internal relative motions of these little constituent elements of the string. Now what about the other term, minus dx by d sigma? Let's work that one out. I think I can erase this. Let's get rid of this for a minute. Let's work it out. How about dx by d sigma? That's not x dot, it's just dx by d sigma. We start with this formula here. That's x. And now we want to differentiate it with respect to sigma. What happens when you differentiate a cosine of n sigma with respect to sigma? You get a minus. Cosine becomes sine, but there's also a factor of n. All right, so there's an n here. Cosine becomes sine. So that's the derivative of x with respect to sigma. Notice if x involves cosines, derivative of x with respect to sigma involves sines. If one is Dirichlet, the other is Neumann, and vice versa. Okay, so now let's write down the square of dx by d sigma. We'll be adding then plus a sum over n and m again, because we're going to square this. When we square it, the minus sign goes away, and we'll have n times m times xn, xm, sine n sigma, sine n sigma, sine m sigma. And this gets integrated. What am I missing? Anything? Yeah. 1 over 2 pi. Okay, what's the integral of sine n sigma times sine m sigma d sigma from 0 to pi?
Same as for cosine. I think it's 0 unless...
0 unless n equals m. And if n equals m? Pi over 2. I heard somebody say it. Pi over 2. Okay, so again, this all adds up. We're constrained to set n equals to m by the integral. The integral will be 0 unless n equals m. Okay, so it's just n squared. Xn squared. Then pi over 2, right? Pi over 2. That cancels the pi and puts a 4 downstairs. So it looks like this, same factor of a quarter, but instead of xn dot squared, it has n squared times xn squared. If we're doing the Lagrangian, it's minus. For the Lagrangian, it's minus. For the energy, it's plus. Okay, so we have 3 terms altogether. The first term involves x naught. The second term involves time derivatives. It's kinetic energy. This is, of course, is also kinetic energy of the whole string. And then there's something which involves x squared. Let's go back to here. This is the energy of a harmonic oscillator. The energy of a harmonic oscillator has an x dot squared and an x squared. Evidently, for each n, the Lagrangian is the Lagrangian of a harmonic oscillator. Okay. The Lagrangian of a harmonic oscillator for each n. What are the frequencies of these oscillators? This system is a collection, an infinite collection of infinite number of harmonic oscillators. It's as though you had a discrete, countable infinity of springs. What are these? Of course, these are just the harmonics of the string. They're the harmonics of the string, and what we've done is to rewrite the Lagrangian in terms of the coefficients of the individual harmonics. And what do you find? First of all, they're not coupled to each other. The nth harmonic is not coupled to the mth harmonic. It's a collection of non-interacting non-interacting harmonic oscillators. What's the frequency of each one of these oscillators? What's the frequency of the nth oscillator? Yeah, n. Right, you can read that off from here. It wouldn't change if you put a 4 here. The frequency would still, in both places, as long as you put it in both places. Omega is the frequency, and omega squared is the coefficient of x squared. Here's the coefficient of x squared, and so we can write, there's a collection of oscillators, each one with a frequency omega n equal to n. Okay. What about omega 0? What happened to it? You realize, of course, that this is the restoring force of the oscillators. This is the restoring, this is the Hooke's law, stretching energy of the oscillator to restoring force. There's no restoring force for the center of mass. Of course there's no restoring force for the center of mass. The center of mass is free to fly away. There's nothing holding on to the center of mass. So there's no restoring force here. That's just x naught dot squared. And the internal energy, this is the vibrational internal energy of the string. It's this which has to be identified, where is it? We lost it, with the mass squared, the true mass squared of the relativistic string, the internal energy. This is the internal energy, and it's to be identified with the square of the mass. Okay, we might as well get rid of this. This is, it's trivial. It's just the overall center of mass motion. This is the interesting part here. And as I said, it's a collection of harmonic oscillators. Now, I've written only half of it. The other half are the y's. So another identical, it's a doubly infinite collection of harmonic oscillators, each one with frequency n. So the first one has frequency 1. It's a nice slow frequency. The next one has twice the frequency. The next one has 3 times the frequency. And of course, these are simply the different harmonics of the string. And what do we do with them? We quantize them. We quantize them. We subject them to the process of quantization, which is very easy for a harmonic oscillator. In fact, we don't even really have to go through the whole exercise. We've done it before. We just have to remember that the energy of harmonic oscillators are quantized in certain forms. Let's see if we can see what the energy levels are going to be. There's going to be a lot of energy levels, an infinite number, of course, but we can make some energies in a, we can start organizing them. I think for tonight I won't write down creation and annihilation operators. And let's, for the moment, suppress y. We'll come back to y. Let's just concentrate on x. Maybe we'll include, let's do y too. Let's do y too. So for each n, there are 2 kinds of oscillators, an oscillator along the x-axis and an oscillator along the y-axis. Okay. All right, so let's see what and they have the same frequencies. The x oscillate, the xn's don't have the same frequencies. The x's and the y's have the same frequency. So there's another replica of exactly the same thing. And of course, they correspond to whether the harmonic is vibrating along the x-axis or the y-axis. By combining them together, you can make oscillations along different axes. Right, so let's see what kind of energy levels the system will have. There'll be a ground state where none of the oscillators are excited. They're all in their ground state. Let's call that O, ground state. This does not correspond to the vacuum. It doesn't correspond to an empty space. It corresponds to a single string with no energy excitation. Right? So it's a string. It's a form of particle. It's got an energy. It's got a momentum. And it has a gap in its spectrum. It has a gap to the next energy level because harmonic oscillators have gaps to the next energy. The quantum harmonic oscillator, it takes some energy, some finite energy to excite it. So it's a particle. All right, what's the first excited state? The first excited state you can create by creating 1 unit of x energy. How much does that correspond to? It corresponds to the frequency. Remember, the energy levels, I should write down a formula. The energy of a harmonic oscillator is equal to n h bar omega. Omega, this is different n. Number of quanta, what shall I call it? Q, number of quanta. Number of quanta, it's an integer. It's an integer. Different integer than these integers. These integers label different oscillators. But each oscillator itself can be excited. All right, so we take the energy of a oscillator is q, the integer q, times the frequency. We're going to set Planck's constant equal to 1. Let's forget Planck's constant. Set it to 1. And omega is just n. So for the nth oscillator, it's just q times n. Okay, for the nth oscillator, the energy of the nth oscillator. All right, so what's the first excitation? You can excite either the x or y oscillator, the lowest oscillator, the n equals 1 oscillator. You can excite it one time. You can give it one quantum of energy. Okay. How much energy does it have then? Q is 1, n is 1. It has 1 unit of energy in some units. We haven't specified units yet. So whatever the ground state is, there's 2 states above it. 2 states above it, whatever the energy of the ground state, let's not specify the ground state energy, it is whatever it is. Above it, this is the ground state. Above it are 2 states. Why do I say 2 states? Either x, you can excite it along the x-axis or the y-axis. It just corresponds to the string vibrating or to the first oscillator vibrating along the x-axis or the y-axis. And of course, linear superpositions of them can vibrate along any axis. So that's the first thing, 1 unit up. 2 states, a multiplicity of 2. I'll put here the multiplicity. The multiplicity of this one is unique. The multiplicity of this one is 2 possible orthogonal, 2 possible states. What comes next? Well, you can do a number of things. You can excite the lowest oscillator twice. You can excite the lowest x oscillator twice. You can excite the lowest y oscillator twice. You can excite the lowest x oscillator and the lowest y oscillator each once. But what else can you do? You can excite the second oscillator. We'll work this out more carefully next time when we introduce creation and annihilation operators. But you can excite either the x or the y, the lowest oscillator once. That will give you 2 units of energy up here. Or you can excite the x lowest oscillator once and the y lowest oscillator once. That will also give you 2 units of energy. But you can also excite the second oscillation once, either x or y. That will give you 2 more. So altogether there are 5 states here. 5 states, x excited twice, y excited twice, x once, y once, or the second oscillator of either the x or the y type twice.
Only 4.
I got 5.
1 and 1 is...
Okay, so let's count. Let's see. We can take in terms of creation and annihilation operators, A for x, B for y. Now we can take the lowest oscillator, A1, twice, squared. B1 plus squared on O. This is exciting the x oscillator twice, the y oscillator twice. A plus 1, B plus 1, O, that's 3. And next, A2 plus or B2 plus. Oh no, 5 states, right? 5 states. Right. Exercise, count the next 2 levels. How many states are there altogether? And it's an exercise for the next time. But the point is, the most important point is that there are gaps between significant gaps between the states. So they're discrete, they're particle-like. We'll work out in a little more detail the spectrum, and then, having done all of that, we'll try to identify some of these particles. Some of them are bad guys that we want to get rid of. Others are good guys that we recognize and we say those are particles that we like. Having done that, we'll want to do closed strings. Let me just tell you right now, in the next 5 minutes, or next 2 minutes, what the relationship, these are called open strings. They're open strings because they have ends. All right, they have endpoints. Now, the basic process of interaction of string theory is string ends coming together and joining to make longer strings. Strings can come together, if you like, in the context of hadron physics, meson physics. The strings have quarks at the ends, quarks and quark antiquarks. Now, that's not true for the string theories that we're going to be interested in, but for ordinary hadrons, quarks and antiquarks. And what can happen is a quark and an antiquark can come together, annihilate, and create a longer string. So the basic interaction process, which we haven't taken up yet, we haven't discussed it yet, is the joining and splitting. If joining can happen, splitting can happen. Joining and splitting of strings. Now, here's a string all by itself. And as it happens, this string executes a fluctuation which happens to bring the other end around close to the original end. This end of the string over here sees another end of the string over here. It doesn't know it's part of the same string. All it knows is it's found another string, another end to annihilate with. So once you introduce string interactions, you are committed to something new. You're committed to closed strings. Every theory of strings always has closed strings. You can write theories of closed strings that don't have open strings, but you can't write theories of open strings that don't have closed strings. So there's something more general. Well, I don't know if the right word is general. There's something, if you had to make a prediction about string theory, it would not be that there are open strings, but it would be that there are closed strings. There's no way around the closed strings in string theory. There are ways around the open strings. So the next thing we're going to have to do after we work out this and figure out what open strings are like, we're going to work out closed strings. I will tell you the answer right now. Open strings often behave like photons. Closed strings behave like gravitons. There is no theory of strings which doesn't have gravitons. There are theories of strings which don't have photons, but we'll come to that next time.
For more, please visit us at stanford.edu.